Okay, hello everyone. Good morning, good afternoon, good evening, wherever you are. Thank you for joining the Geoscience and Geoenergy webinar of today, 12th of May 2022. Today, Sebastian had some work duty and couldn't really attend at the final minute, so I have the pleasure and honor to host you all together with our distinguished invited speaker, Professor Tannaz from Teesside University, UK. Tannaz is a senior lecturer in energy and environmental engineering. She holds the Chartered Engineer status and is a professional member of the Institute of Materials, Minerals, and Mining. Her research is mainly focused on porous materials in different applications, including environmental remediation, water purification, and energy storage. In 2021, just last year, she was selected as one of the top 50 women in engineering by the Women's Engineering Society in the UK. So quite impressive. Prior to starting her academic career, she did a PhD in geosciences at the University of Edinburgh in Scotland in collaboration also with Heriot-Watt University. She has done her MSc in reservoir geoscience and engineering at the IFB School in France and also obtained her bachelor degree in engineering from Iran. Thank you very much, Tannaz, for graciously accepting our invitation to offer this lecture despite your extremely busy academic schedule. And to the audience, please note Tannaz's lecture will last for about half an hour, followed by questions and discussions. And I'll pick up the questions and hold the discussion session after the webinar. Please do not wait until the end of the talk to ask your questions. Whenever you feel appropriate, please do text them. Your question will motivate other colleagues to get engaged and post other questions. So without any further ado, Tannaz, the stage, bandwidth, the screen is all yours, and we are very much looking forward to hearing your talk.
Thank you very much, Hadi. This is a great pleasure to be here today. And I'm going to talk to you about groundwater and new methods, new technologies to remediate contaminated groundwater. First of all, I'd like to acknowledge and appreciate the contribution of my teammates whose name is listed on this slide. And also we've received financial basically support from the agencies. You can see their logos on this slide. So thank you to all of these people who supported our research. I'd like to start from just overviewing groundwater contamination and looking specifically at chlorinated solvents as a specific source of contamination. Then I'll look at groundwater in the UK and in Brazil briefly. And to fit everything in half an hour, I'd very quickly look at nanoremediation as a technology. Then I'll want to show you a specific case study that we looked at pore scale processes behind nanoremediation at really small scale. And then very briefly look at the reactive nanoparticles mobility in porous media. I'll have to just go through this very quickly at the end and then making a few conclusions. So many of you will have seen this before, so this is nothing new. The Sustainable Development Goals set by the United Nations. Most of you will have aligned your research to one of these themes or a number of these themes. This research that I'm presenting is looking at the sixth goal, the clean water and sanitation, trying to contribute to that, and also looking at the third goal, that's the good health and well-being. Especially, we're looking at groundwater, and we know that more than 2 billion people globally rely on groundwater as their primary source of water. And we know that groundwater is sadly contaminated as a result of human activities at the surface. And we know that that has been linked with basically health issues experienced by communities around the world. So specifically, I want to talk about chlorinated solvents. These are a family of contaminants that you can, I've basically put some of the chemical structures of some of these on the slide for you here to look at. So these are a family of substances that actually are synthetic, so man-made. These do not occur naturally in the environment. They have been in use since 1920s when we started actually producing these. These are really nice solvents, really nice degreasers. So they've been used abundantly in industry in general, in manufacturing, in metal processing, in basically businesses like dry cleaning. So very much in use. Up until 1950, they gained quite a lot of attention as nice solvents in industry. So that was the peak of their use. Then we started gradually to realize that they do actually pose quite significant health risks, and we were able to actually link them with a number of adverse effects, including, for instance, kidney and liver damage, and some of them started to be recognized as carcinogens. So we then started to think of replacing these, but it took us quite a while in order to actually be able to, at larger scale, replace the use of these substances. Now, in the EU in 2016, a ban came into force, and we no longer use these substances at large scale as solvents that we then would have to basically deal with and dispose of. But at the moment, because of their extensive use in the past century, we are now looking at contamination, serious contamination globally, and the damage is done. And we now need to look back and try to find techniques and methods in order to basically remediate groundwater that's contaminated by these. Now, what typically happens is that in the past you would have had factories and sites where these solvents would have been in use, stored at the surface, or basically just dumped to be evaporated because these are volatile after they were used. So if that happens, if there is a leak at the surface, then because these contaminants are denser than water, they would find their way in layers just underneath the source of basic contamination, and then they will basically penetrate through layers and find their way into the groundwater. They will then create a source of contamination there. If you look at the sediments, there you'll see that these form droplets or clusters, because these are also very much not so much soluble in water, so only poorly soluble. The solubility is in the order of grams per liter. So they form droplets in between the sediment grains, and what you then will need to do is that to find a technique to try to basically remove the source of contamination, because what will happen is that because groundwater has a natural flow to it, it will then carry the contaminant downstream and will then form a bigger area, contaminated area, that we call a contaminated plume. Now, the amount of these substances that we now want, to the threshold amount that we now want to have in our water and still be able to drink it, is the order of microgram per liter. In the EU, it's about 10 microgram per liter. Some countries, it's even less than that. So you can start to imagine that only a small amount of these contaminants can actually render quite a lot of water unsuitable for drinking, and for a long period of time, decades in many cases. So we now need remediation technologies to remove these contaminants. Traditional technologies include, for instance, just go and dig all of the soil and contaminated sediment that's basically affected by these contaminants, and try to basically move them to a landfill, or try to apply some technologies to remove and clean the sediment and soil. This is quite a bit difficult now because of the expensive landfill charges that we are dealing with going forward, and the waste issue that's we are globally facing. The other technique that's very conventional is pump and treat as well. So you take, in this technique, you take the water, pump the water out, and try to deal with the water at the surface. So this is an ex situ sort of technique, but this is also not that suitable because you're dealing with quite a lot of energy to do that, and it's never totally effective because there's always some remaining amount of contaminant in place. There are also other techniques, more advanced techniques that are trying to offer in situ solutions. For instance, you can have the option to inject some chemicals, some oxidizing agents or reducing agents in order to promote the chemical reaction in situ, and in order to try to deal with the contaminant subsurface and not disturb what's happening at the surface. These have been really successful, but they have some specific challenges. For instance, sometimes the chemical reaction can actually produce some solid phase, and the solid phase would clog the pore system, and the continuation of that process is typically sometimes difficult. You can also look at bioremediation, in which you are now relying on microorganisms to degrade the contamination in place. This is a technique that is naturally happening in process, but sometimes you try to accelerate this because naturally this is quite slow. So this is something that has been applied with good success, but it's a very difficult system to put in place and manage. There are other newer, more novel techniques that use advanced material, the likes of activated carbon and nanoparticles, metal nanoparticles. The specific one we are looking at today is a use of zero valent iron nanoparticle to deal with these type of contamination. So I just wanted to show you a project that we had with a number of Brazilian institutions, universities involved, as well as university in Italy, Polytechnic of Turin. We had this project together for a few years, and in that we tried to look at understanding if nanoremediation can be applied in Brazil to deal with groundwater contamination in Brazil. What we did in the first was to try to look at what is happening at really small scale, at pore scale. And we did a series of experiments at the Brazilian synchrotron back in 2018 in order to look at the pore scale, basically mechanisms behind nanoremediation. You can see a picture of a group of interested scientists and industrialists who gathered together in a conference we did in 2018. We repeated the conference as well, and we realized that there is a community of interested audience in general in terms of learning more about nanotechnology and seeing if this can be applied to Brazil. In the second phase of this project, we were planning to look at applying the first pilot scale nanoremediation case in Brazil. We did go through quite a few steps with this, but in the end, because of COVID, this actually didn't happen. So we didn't actually apply nanoremediation in Brazil, but we did go through quite a few steps in terms of preparing, looking at a number of sites, contaminated sites that were really good cases for this technology. We also worked with the environmental agencies, both the federal agency and the Sao Paulo's environmental agency, to see and explore if Brazil is ready. And as part of that, we submitted an application to look at zero valent iron nanoparticle as a substance that can be applied subsurface. So here you can see that just before pandemic, I had the opportunity to visit Brazil. And here, for instance, you can see us standing on top of a number of monitoring wells that the environmental agency of the state of Sao Paulo has in one of the contaminated sites, which is within the suburbs of the city of Sao Paulo. Now, in order to understand how the groundwater contamination situation at the moment is, in addition to the immense experience of our partners in Brazil, we also relied on this groundwater, on this registry of contaminated sites that is published by the CETESB, which is the environmental agency of the state of Sao Paulo, every year. So the registry goes back to 2002. It's published every year. It's basically a record of all the contaminated sites. The format is not so accessible, so it's a very long PDF. So this is how it would look like if you open one of the PDFs. You'll see that the PDF, it has thousands of pages. Every page is looking at one contaminated site. So this is obviously in Portuguese. So our colleague Daphne kindly has. Let me just click here. Yeah, here translated this to English, so you can have an idea of what sort of information you can find in this registry. So obviously you can have an idea about where this contaminated site is, but also you can have an idea about what is the stage at which this site is. Is it just being assessed for contamination? Is it going through a remediation activity? Has it been basically closed because it's all remediated now and it's now being just monitored by the environmental agency? So you can have those information. You can also in the bottom see what sort of remediation techniques have been applied to this specific site, but also you can have an idea of what type of contaminants are present at this specific site. So quite useful. What you can see is that obviously there are no measurements, so these are only tick boxes. And to look at all of the data, my PhD student Nuha has managed to actually develop computer code to digitize this data. And based on that, and we're only looking at the data from the 2020 report, you can see that this is in one, basically in one view, what you are going to see if you look at that 2020 report. So you can see about 70% of the contaminated sites are just gas station, petrol stations. So contamination coming from hydrocarbons. Specifically, about 20% of those sites are industrial sites, and these are more or less the ones we're wanting to look at. In the bottom, you can see a map of the state of Sao Paulo. You can see the dots representing the contaminated sites, and obviously a lot of them are focused in the city of Sao Paulo itself, so because of it being very much industrialized. And also you can see some of the dots that are going out of the state, and these are the main highways going out. So these are the gas stations basically going out of the city. So if you look at the range of contaminants that you can see in overall in the report mentioned, you can see that I'm here highlighting the chlorinated solvents in red for you. So putting all of these together, you have just below 15%, about 13% of the entire contaminated sites that are contaminated by chlorinated solvents. But if you look at the industrial part, that 20% that we are interested in, and adding all of these three columns together, you'll find that just about 50%, just below 50% of the contaminated sites in the state of Sao Paulo have reported the presence of chlorinated solvents, which makes this problem really significant for Sao Paulo to solve. I just want to put this also into perspective by showing you what's happening in the UK. Here, I'm showing you the map of England and Wales, and this is from the data that DEFRA publishes here in the UK, and the Environmental Agency of the UK publishes. There are actual measurements in this report, so we can have a better look at what's happening. So on the top left, what you have is the map at in the year 2000. And what you can see is that you can see the level of PCE in groundwater, and you can see there were hot spots back in 2000, and you can see the range. So these are values much higher than what we really want to have in our water, going up to 4 milligram per liter. Fast forward about 20 years, and what you can see here is that the level of PC in groundwater has dropped quite significantly. Not only the basically regions are a lot less pronounced here, but also you can have a look at the scale and see that the scale is actually about 10 times smaller as well. Same story with TCE. We've had a number of cases. So these are linked with specific incidents where a large amount of these substances were released. So you can see that there was quite a lot back in 2000, and now we have a lot less problem dealing with these substances in groundwater. However, this shows us that there is still some problem to solve because of basically the remaining residual amount of chlorinated solvent in the UK's groundwater systems. Now, let's look at nanoremediation. So the technology, one could talk about this for hours, but I'm just wanting to say the basics. So the technology involves taking nanoparticles of iron, in this instance, that are kept at zero valence, so Fe0. This is abundantly available element and not harmful at bulk scale. So you take nanoparticles, you suspend them in water, you try your best to have a good suspension, and then you inject into subsurface where you expect to see a distribution of the contaminant phase, similar to what I'm showing here. So the bright phase is the contaminant phase, could be the TCE, PC, or similar contaminant, a DNAPL phase. And if you look at 3D renderings of these droplets, you expect to see something like this. So these contaminants are, as we mentioned, not so miscible and not so soluble in water, so they'll stay there for long term unless you actually do something about it. So your idea in this nanoremediation technology is to try to promote a reaction, a chemical reaction like this that I have on this slide. There could be many similar ones, and in that attempt you're trying to basically react the chlorinated solvent with the electron that comes from the iron phase in presence of water, and try to basically degrade that chlorinated solvent into something that's not harmful. So when we looked at this reaction, I realized that actually if you go through this successfully, you're going to go from a DNAPL phase to a gas phase, and not only you're actually removing this contaminant, but also you're creating quite a lot of gas that may then impact the arrangement of fluids within the sediment. So that may in fact help you move some of the trapped contaminant phase. So this is a proven technology. It's working at small scale, large scale, but it's far from optimized because there are knowledge gaps. So we identified those knowledge gaps. So what I want to now show you is part of what we've published in back in 2020 in this paper. I also wanted to mention that there are two other papers that we published in the past in which we look at non-reactive nanoparticles. So if you're interested, you can have a look at these other two papers, and specifically this data set that you can download for free and do your studies on those images. Okay, so in doing this experiment, the Pore scale study that I mentioned, we are applying the non-destructive 3D and 4D imaging that uses X-ray tomography. So to do that, you probably have heard about this, or even you probably have done a CT scan at a hospital. This is the same technology. You could take a sample, you could basically expose it to X-ray photons, and you could basically grab projections of that sample on the camera that is part of the system, and then you can basically take hundreds of these, put them together, and create a 3D image. The technology works the same if you use a benchtop scanner or if you go to a synchrotron facility. The advantage of synchrotron facility is basically the better time resolution, so you grab images much faster. So the idea is to collect those projections, put them together, create 3D images, and then look at those 3D images in order to not only just visually see the phases you're interested in, how they are evolving, if you're looking at a time series, but also be able to quantitatively analyze them, specific phases, specific parts of the specimen you're investigating. Now, the idea here, and I have to say and give credit to the project Nanorem that inspired me quite a lot. This was a very large project, European project, that looked at taking nanoremediation from the lab to the field scale, quite successful project. When I looked at all the reports they published, I realized that this is something that we can actually study quite well using pore scale imaging that we have applied to many other geosciences related projects. So what we have done, the hypothesis we had was that because of the reaction I showed you, because of the fact that we're producing some extra gas phase, that gas phase can potentially help us overcome the capillary trapping and help remove the source of contamination. So in order to investigate that, we looked at running an experiment at the Brazilian synchrotron, the IMX beamline, X-ray tomography beamline. So this is a column that we had, obviously small scale column for this type of experiments. And we packed that with beads, quartz beads, glass beads. And we then basically placed that on the rotary table of the CT machine. And what we did was that we started injecting a number of fluids in a sequence and grabbed images as we did that. So first of all, we basically saturated the bead pack with water, only water. Then we injected the TCE. So the contaminant phase that we are looking at here is the TCE, trichloroethylene. So we looked at injecting that, and then we basically flushed everything that was mobile outside the pore space by basically a water injection following that TC injection. Now, what we then at this point, you have droplets and clusters of TCE that are now basically waiting. They're basically trapped. They're in need of remediation. So what we then did was that we started injecting the nanoparticle suspension, and we then looked at what is happening to the remaining TCE phase. Okay, so this is a picture of the setup, this is the column that we put together, packed with the beads, and this is part of the team. I'm happy at the end of the experiment. I'm now going to jump over all of the calculations and all of the processes that we had to do in order to extract the results from the images we had. It took us about a year and a half to get to this point, but eventually this is what we the result of this experiment tells us. So I'm here showing you the TCE phase in red. On the top left corner, you see the time at which these images are taken. What we started off with was, and on the top right, left, you can see the amount of TCE in percentage that we have seen in that image at that particular time. So what we can see is that we started off by having 12% TCE in the field of view, the bit that we were imaging, and we started injecting the nanoparticle. It took some time for the nanoparticle to actually arrive at the field of view we were looking at. By the time it arrived, because it's a viscous fluid, it actually had managed to remove half of the TC outside the field of view, so that's all right. Then we started just watching what's happening as a result of that reaction that we were trying to facilitate. So we started to observe the formation of a gas phase that I'm rendering here in yellow for you. So the gas phase started to emerge and start to come into the field of view we're looking at. Then we did another round of nanoparticle injection. This is what is typically practiced at field scale, a two-stage injection. As a result of the second injection, we realized that there has been quite a lot of gas formation that is now flowing into the field of view, and as a result of that, the remaining TCE within the field of view has dropped to 2%, the lowest amount in the experiment, which is quite substantial, going back to the discussions I had. So we also were looking at the pressure, and the pressure response was also telling us that there is, so this is the initial injection, obviously you expect to see some increase in pressure, but we when the gas was formed and when it was being moved, we noticed quite a lot of instabilities in the pressure, which suggests that you have gas in the system. Okay, then we looked at what is actually happening pore by pore and what is actually happening to the TCE, the trapped TCE droplets. We could identify two specific pore scale mechanisms. The first one we looked at as gas formation and flow, and the second one was actually the first time this was suggested in the literature, and this is where a droplet of TCE was being degraded at the interface that it had with the nanoparticle. So I'm here showing you two examples of the first pore scale mechanism we identified. Here you can see two droplets, one droplet and a larger cluster of TCE that is trapped in between those spheres. It's not moving as a result of nanoparticle injection, but when it comes to actually gas formation and flow, that remobilization of fluids that we had in our hypothesis actually shows quite well here that gas is in fact capable of displacing the residual TCE phase out of the pore, initially confining it and trapping it. And these are just slices through these droplets and clusters you can see here, just to show you what the images actually looked like. So the sparkly phase is the nanoparticle phase here. This is the TCE phase that's now being pushed outside the pore, confining it as gas comes in. So here, quantitatively, you can actually see the amount of TCE left in the box where I'm showing you as a result of this gas formation and flow. This is for these two examples, but overall, when we look at the image itself, it was about 57% removal of TCE, which is quite substantial. The second pore scale item that we looked at and we realized was that for some of those droplets that were persistent, they were not moving as a result of the nanoparticle injection or water injection. The day after we took all the images and we gave time for the reaction to develop, we realized that at the point where the nanoparticle phase was basically in contact with the droplets, we could see development of basically degradation of this TCE droplet. When we started looking at the rate at which this was happening, this proved to be quite a lot slower compared to the first displacement mechanism that I showed you. Nevertheless, this was something that was reported for the first time, and this would help actually thinking about applying this nanoremediation technology closer to the source rather than to the downstream. The other thing we looked at was looking at the permeability of water as a result of having gas in the system. And we thought before the calculation was that if you have so much gas in the system and the gas is non-wetting phase, obviously would tend to occupy the bigger pores. So that might actually help basically limiting the amount of contaminated water spreading, and this might prove actually an advantage. And this is what we came to realize as well. You can here see only the water phase at different points, and here you can see the water permeability. This was calculated using the image, using Navier-Stokes equation. What specifically you can see is that the black here is permeability. So permeability reduces from about 60% down to less than 1% when the gas starts to emerge and occupies the larger pores. So this is a benefit because it basically controls the mobility of contaminated water. So then we took the experiment to the diamond light source. This experiment was in August 2019, a repeat of the experiment we did. We still have this data to look at. We've looked at it a little bit, but this is a massive data set. We had a larger sample. We had higher energy available at diamond. We had a better contrast between the phases. This time we looked at sand instead of glass beads, a more natural system. So we looked at basically repeating the experiment, and so far what we've realized is that the gas formation and flow and the changes in TCE arrangement is there. We've been able to confirm that. We still are looking at this It's a huge data set. So we took about 62 terabytes of data in 4 days. So quite a lot of work involved. So last thing I want to talk to you about is the study we are doing on just looking at mobility of nanoparticles in porous media. This is the work we're doing with people over in Turin. They have developed a model that looks at basically mobility of nanoparticles in porous media. We wanted to look at a pore scale imaging study in order to see all of the mechanisms they have assumed is happening in the model, if we can basically inform that or add something to that. So specifically, we're looking at reduction in porosity, increase in surface area, reduction in permeability. So typically what you would do is that in order to study mobility of nanoparticles in porous media, you take a column, you pack the column with the sand you're studying, and then you inject the nanoparticles, and you look at what's coming out, and you try to understand overall what's happening within the system, and you try to form what's known as a breakthrough curve, and then understand what sort of basically particle entrapment was happening in that column. What we did was that we took a sand pack and we looked at performing an experiment like the one I explained to you. I don't have more time to actually go through the details of this experiment. I do have an Interpore talk. Interpore is coming up. If you're interested, you can, and you're attending Interpore, you can watch that. But the idea is just to look at injecting water, injecting nanoparticle, and then removing nanoparticle with water, and try to look at images and quantitatively analyze them and understand what we can understand from the images. So here you can see we can plot the grain size distribution, pore size distribution, the surface area of any of the phases we're interested in. So we did this experiment again at IMX Beamline in Brazil, and it looked like that the particles, we had an initial good saturation. So this is the particles in between sand grains. We removed the mobile particles with water, and what we could see was that the particles that were remaining were mainly trapped within the pore throats and pore corners. So we're trying to now study this and see what sort of reduction in permeability we're getting. We haven't done that yet, but we have looked at the sort of size distribution of the nanoparticle clusters. Obviously, nanoparticle clusters are mobile. That's what we've seen. And they are occupying pore throats, so smaller nuggets compared to the pore size distribution. That's what this plot is showing you. And the other plot on the top is showing you the surface area of the nanoparticles, quite an important parameter if you are trying to promote a reaction. So that's showing you that the surface area of the nanoparticles is quite a lot higher than the sand itself, which is something that that is pleasant. That is something that you'd want to have a higher surface area. Okay, so in conclusion, and I think I took a little bit more time, I want to go back to my initial point. We are looking at groundwater as a valuable resource that is supplying water to more than 2 billion people globally. We have managed to contaminate the groundwater in many places. We are now in need of better, more effective remediation technologies. Nanoremediation can be one of those technologies. There are things that we can learn from small scale, pore scale, and if we look at that scale, we can probably design better, larger scale processes and be more effective at large scale. If you're interested in any of what I discussed, please do get in touch. I would like to thank Hadi and Sebastian for inviting me, for giving me this chance to talk to you. It's a pleasure. Thank you very much.
Thank you very much, Tannaz, for this extremely informative and engaging talk. I lost the track of time, but you are slightly over time. So now I realize what is late. I cannot stop you. You're already done. So let me.
I am always like
So
that. This is the thing with me.
that's very nice. But that was really a good talk and really nice. I have plenty questions posted. I'll start with actually the last one because it is correlated with the last topic that you addressed in your talk, and it's from Sarah, and she's asking after thanking for your question is about her question is on the trapping and migration of contaminated water. If they form trapped clutters, can they still migrate to the, from the source? And what factors aggravate migration?
This is a very relevant question, because one of the challenges of applying this technology subsurface is it's to do with the mobility of nanoparticles. Although they are meant to be nanoparticles, but in practice they actually form clusters, so that their actual size is larger than a nanoscale. And obviously, depending on the type of nanoparticle you are applying, and the medium you're applying this nanoparticle to, you'll have a different amount of mobility problem and entrapment problem. And this is what we were trying to look at in the second study that I showed you. But there is definitely a challenge in terms of particles being mobile, and particles being mobile from the point that you inject and getting them to the point you actually want them to be. And this is more problematic with larger scale particles. So for many years, we applied micro scale zero valent iron, but that is totally immobile. So it's just applied where it needs to be and it cannot move. It's obviously a very limited movement. But the nanoparticles are a lot better than that, but they're still problematic. So yeah, I think you hit the nail on the head.
Thank you very much. Yes, and she continues asking the second question, also asking what happens if the contaminated areas are just left untreated? Would uh, the contamination stop itself, or natural phenomena would help decontaminate?
Yeah, so typically remediation activities are conducted in campaigns. So you'd go in, you calculate how much reagent you need. It could be just a chemical reagent or a nanoparticle. You perform what you need to do. Then you look at what's happening with the levels of contaminant in the water that's coming after a while. So what you're hoping is to have been able to reduce that, but it's not as easy as that. Geological systems are very complex. There's a part of the contaminants is always basically attached to the media itself, so that might start to get detached and desorbed. So there's always remaining bits that you might need to go back and do another campaign to try to remove everything. But at every stage, you try to reduce from where you were. That's my understanding from what the question is saying.
Okay, thank you. And I have many good questions, but I like to give them some sort of a storyline so that you step in a logical manner. So Willemijn van Rooyen is asking, after taking thought, that where are these contamination issues most likely to take place? You went to Brazil, and people would wonder why did you go to Brazil? Or you showed the England also map of contamination. What's going wrong there, and how is it that some places are highly concentrated with contamination, other places are safe?
So, in general, one word is industrial areas, places where we have been using this contaminant, the solvents that I discussed, as at a larger scale, in our process, in our activities at the surface. And it's been really worldwide. In the US, there's quite a lot of significant problem around eliminating chlorinated solvents, and they've got specific projects at national level, dedicated funding to just deal with this. But it looks like that wherever you've had at small and large size, basically industrial sites where these have been in use at some point in the past decades, they could be a site that's contaminated. So that's why environmental agencies go into different sites. They put monitoring wells in place. They try to have a record. But sadly, they've been in use at really large scale for many
Okay.
decades.
Mhm. And she's asking about perhaps 3D distribution of this contamination. What you showed, for example, in the slide 11
Yeah.
was kind of a 2D plot. Do we have in-depth concentration understanding of the contaminations,
Slide
or is it?
11. Right. Let me just go back to slide 11 to know what exactly. Oh, so this is one of the maps, right? Probably
Yes,
one.
exactly. UK map.
Yeah, so
Yes.
this would be a very thorough thorough investigation to look at having a 3D map, because then you'd need to look at every site, and you
Mhm.
need to look at the hydrogeology of that site. And this is what we
Mhm.
were trying to do with those two specific sites in Brazil.
Mhm.
My partners had lots of experience of for many years working with those specific sites. They had the maps, they had results from so many years of going back to those monitoring wells. So that would be an immense project to look at everywhere. But there are specific, basically, you could look at every contaminated site, and you could be looking at dedicating
Mhm.
time to understand what's happening in 3D.
Thank you very much. So I would jump a bit of a few questions and come to the other questions, so the audience will notice that I'm not following the order in time, but on the topic. Now we addressed the topic of where could they happen, urban areas, industrial areas mostly, and so.
Yes.
Herminio is asking now towards the other side of it. It's about how can we resolve it. This is a very important topic. In your opinion, what could be a feasible approach to implement this remediation strategy in practice? And maybe the next question that is also following up is saying that implementing a chlorinated solvent management policy for each gas station, for example, would be a kind of a practical uh, practice that we can resolve this contamination process. Or what do you think it would be working in practice?
This is a very good question as well.
And
And
Herminio is coming from Brazil originally as well, so he's
yeah, no,
so
that's
that's
brilliant. I think one of the things that we need to have first everywhere is to have a ban on the use of these substances, in order to make sure that we're not actually adding to the contamination going forward, and that is happening. That is in place in the UK and EU. I was talking to my colleagues from Brazil to basically understand if this is in fact in place. Some Obviously this is now on the list of hazardous substances in Brazil. So when we were performing experiments, we actually had to ask for permission from the police to actually get 1 liter of this substance. So
oh,
there
is that
is,
right?
yes, and we had to report on what day we took 1 milliliter and we applied. And the
Wow.
experiments I showed you, they might seem simple, the setup and
Mhm.
everything, but because these are toxic substances, we had to design a whole set of solutions around making sure that none of this gets into the air of the environment that we were breathing. So specific, basically, systems in place to make sure that all the air around the outlet
Mhm.
is extracted and all of that. But in general, for looking at solutions, what we have here in the UK specifically is that we're and we have ensured that there's no more coming in as a starting point. But also there's quite a lot of really effective technologies in place now that we can use to reduce the contamination level. And
Mhm.
it's not easy, because in many of those industrial areas, a lot of these industries are actually neighboring each other. And this was the case for one of the ones I visited. And it's very difficult to identify where is the point of contamination, and to really have it sorted in between all those neighboring sites in an industrial estate. But there are new technologies. The technology I'm talking about today is not applied in the UK,
Mhm.
but it is in EU in many cases, in Spain, Czech Republic, in Switzerland. We have many case studies. Over in the States, there are many case studies of this technology. But I would assume that the nature is doing its job. So the bioremediation is active, thermal remediation is active. So in many decades, the nature is going to degrade a good amount of these substances that are in place. The
Matter of being patient, I guess, and allowing
Exactly.
time and
But
scale.
yeah, and also we don't want to leave it to the nature to clean this.
Exactly.
We want to try to
Absolutely.
go in, do some intervention, and it very
Mhm.
much depends on what is really identified as a priority, because these take
Exactly.
quite a lot of funding and resource.
Thank you very much. Actually, I have a few questions that go a little bit technical, but they're also important to be addressed. And we take the chance that you're now here with us to go through them as well. So, I have a
Yeah.
question from Martia Bone asking more about kind of, as engineers, we would like to understand the system in the lab, but go and find solutions in the field. Now she's asking, after thanking you for the interesting and informative talk, what quantities in the lab experiments are you specifically looking to upscale and put it in the right field scale,
Right. So
practices
this
and
is
analysis?
Yeah, so for the mobility case study that we looked
Hmm.
at, this was the question we asked ourselves initially when we were planning for the experiment, because we had this case where one of the partners had a model and we wanted to look at what parameters we want to investigate to be able to feed into that model. So for the nanoparticle mobility, we are looking at running a smaller scale basically experiment using CT, so very small column, but also a larger scale column with the same sand, same sort of media, same nanoparticle, to have the other curves that I showed you, the breakthrough curves, to
Hmm.
combine those and then to inform those larger scale models. So we have a range of scales to play
Hmm.
with. And
Hmm.
especially, for instance, we are looking, as I mentioned very quickly, so the reduction in terms of nanoparticle entrapment, we're looking at the reduction in porosity, reduction in permeability, looking at specifically the surface area. With the images, we can actually also identify if where about the nanoparticles are
Hmm.
trapping and
Hmm.
clogging the system. If
Right.
if you're doing a sequence of injections, first phase, second phase, third phase, is if
Sure.
there's a history of having nanoparticle in a sediment, is that promoting a new pore scale entrapment process, which we have seen in one of our images. So these are the
Excellent.
sort of things we are interested in.
Thank you. I see you as flooding information to us when we ask you a question.
I'm
It's
just,
just a stream is coming, and I'm trying to just catch, some words here and there. It's just amazing
I'm
the path.
so
I have
sorry.
seen your
Yeah,
your PNAS,
overexcited.
what is it? Proceeding of National Academy of Science paper. I have studied that before. It's
Oh,
really.
that's,
I'm delighted that you had this
thank
presentation
you
here
very
today.
much.
I have the next question here. Would combining the porous scale experiment now with a little bit larger scale, like core scale things that we typically also do, would allow us target the same system at different scale and get it a better kind of a scalability analysis? What would you think?
Yeah, so this is exactly, I think this adds to the previous question, and that's
Yes.
exactly what we want to do, because with these very small scale experiments, you can miss a chance to collect, for instance, the fluids that are coming from the column, because they're just such a small scale. We
Mhm.
do manage as much as possible to basically collect all those and try to, but sometimes you just have so much small scale, for instance, fluids samples that you've taken, that you can't actually do much with it. But if you have a
Mhm.
larger scale column experiment, then you can
Mhm.
actually provide quite a lot
I see.
more confidence in terms of, for instance, doing those
Sure.
nanoparticle trapping tests, and
Thank you very
that's.
much. So Kishan is asking, after thanking you for the talk, I assume the field is heterogeneous, both in terms of properties for flow and conductivities, but also chemistry-wise as well. How would we quantify and deal with uncertainty at the real life?
Yeah.
Yeah.
So somewhere in this is also a very relevant question. Somewhere in the talk, I mentioned that we had to develop a screening criteria to select a suitable site,
Mhm.
and these exist. Actually, we're not doing this from scratch. This is what we were doing in collaboration with our industrial partner, who's doing this in multiple different countries. But specifically, we were looking at what type of environment we have in Brazil, and in those two specific sites. So we have a range of parameters that we want to avoid in order to have this technology successful for the nanoparticles to move, to be able to be applied successfully. So,
Mhm.
for instance, having clay in subsurface layers, that causes problems. Obviously, they are very fine structured. If the clay is contaminated and the contamination phase is actually sorbed to the clay phase, then you're expecting to go to have a long term sort of source of contamination being released from that sort of clay phase. So but you wouldn't go ahead and do apply nanoremediation to a clay basically layer. You'd
Mhm.
want to have
Mhm.
a layer that's prepared, that's
Sure.
basically a medium size basically sediment that's not posing a lot of risk in terms of nanoparticle entrapment in the first place.
Okay. Very well.
In,
I have another question. Tannaz, if I leave you, you will continue
yeah,
to
yeah, yeah,
reply.
you have
There
to
are
stop.
many questions. I need to just do this justice, and I'm sorry if I'm not taking all the questions, but this very last one I would like to take, and that is which soils are typically easy to remediate and which one are not easy? And could you explain what is causing these differences?
Right. So I'm not a
Yeah.
soil scientist, I have to say, but this adds nicely. I think I can see the storyline you're trying to put together
Mhm,
is
mhm,
working. This adds on to what we just discussed. So this we're first of all we're not applying this to soil. We're applying this
mhm,
to sediments because applying this to soil would be very difficult. Soil doesn't it's not a consolidated system, so if you were to inject and increase the pressure, then
mhm,
it will emerge, it will surface a few meters
mhm.
away from where you're injecting. So
Yeah.
we're not proposing this as a solution for soil remediation.
Mhm,
We are
mhm.
looking at subsurface and a good depth, not too deep, not too shallow, in order to make sure that we can actually control the movement of particles.
Yes.
So, but again, things that I mentioned in terms of environmental conditions in general would contribute. Added to the clay that I mentioned, it's the salinity of water, background salinity of groundwater, and that's also going to play an important role in terms of having the particles, their zeta potential, and how much they might clog, they might
Mhm,
basically come together, form flocks, so
mhm.
making their life more difficult in terms of mobility. So that's something else you want to look at, the background groundwater salinity.
And I'd like to take the opportunity as the host of you, the proud host of you, to ask my also burning question.
Oh
You
no.
can stop, you can solve this extremely, my mind is so engaged through the talk that the storyline that you presented. I'm thinking two way. Is it easier to stop from the source to avoid contaminations, or it is much better to fix it? Is it that way that we can predict in global picture? Where are we moving to the right direction globally to avoid the problem from the beginning than to
Mhm.
find solutions for it?
So I think if we have awareness a lot
Mhm,
better than many decades ago. We know the source of contaminants. We have good monitoring systems in place. If I go
mhm,
back to the registry of contamination in Brazil that has started from 2002, if you look at the initial reports, they were hundreds of pages. Now there are thousands and thousands of
I
pages.
see.
There are monitoring wells already in place
Mhm,
that have happened over the past 20 years, that environmental agency has actually worked with contaminated site owners to put those in place. So the way forward is that we can now look at what we have, really have a good idea of the level of contamination, how the contamination is evolving over years. So we are
mhm.
in a much better position, I would
I
say,
see.
from my
Mhm,
understanding. This is my understanding compared to, say, 50 years ago, where we
mhm.
knew these contaminants are linked with health impacts. We knew we shouldn't be
Sure.
using them, but we were not there yet.
I see.
And also add to that, we have a range of good, effective remediation technologies. But
Technologies.
funding
Excellent.
remediation projects always problem. Um,
It's
so
never
that
enough to discuss about this absolutely important, crucial topic, and we are delighted that you are leading this research also.
thank you
And
very
I
much.
am enjoying reading your articles and studying them. As I said, the Pinas article, I really it took my attention a bit. So I'm
Thank
really delighted to have had the pleasure of hosting you today with us. Thanks a lot for sharing your wise words on the subject, and I hope that it also causes our audience to get to also pay some research attention to this extremely important and impactful topic on water resource management. So, with that, I'd like to just take the chance to introduce our next week's speaker. Next week, we are going to host Professor Serve Kamrava from the University of Wyoming. Serve will give a talk about machine learning for modeling complex materials. Until next week, 19th of May, 4 p.m. Central European, 3 p.m. British time, 7 a.m. California. Stay happy, healthy, and tuned into our channel for another geoscience and geoenergy webinar. Thank you very much, Tannaz. You were the 103rd speaker
Oh,
of our channel.
that's brilliant to know. Thank you as
All
well
the best, everyone.
for the
Goodbye.
invitation.
Bye bye, everyone.
Thank you.
Bye.